Right now, somewhere above you, there are galaxies so far away their light hasn't reached Earth yet. And it never will. Not because they're too distant, because space itself is pulling them away from us faster than light can cross the gap. That fact alone should unsettle you. But it's not even the strangest part of this story, because everything you're looking at, every galaxy, every star, every atom in your own body, was once folded into a point smaller than anything you could picture. No width, no height, no inside or outside, just a single, impossible concentration of everything that would ever exist. Physicists have a name for it. They call it the singularity. And the honest truth is this: nobody knows what caused it to let go. What we do know is what happened in the moments after. And what happened in those moments would decide whether a universe like ours could exist at all, or whether it would collapse back into nothing before it ever began. This is the story of that decision. It was made in less time than it takes you to blink. Before there was a universe, there was no before. Time itself is something the universe had to create along with everything else. So when scientists talk about the beginning, they're not describing an event happening somewhere. They're describing the moment location itself became possible. At the earliest instant, physics can currently describe all the energy that would ever become matter was compressed into a state so extreme that our known laws simply stop working. Temperature loses meaning. Distance loses meaning. It shouldn't have been able to do anything but stay exactly as it was. Instead, it began to expand, not outward into some pre-existing empty space. There was no space to expand into. Space itself was being manufactured, instant by instant, everywhere at once. Scientists call this era inflation, and the numbers involved are almost impossible to hold in your head. In a fraction of a second, the universe is thought to have grown by a factor large enough to take something smaller than an atom and blow it up to the size of a grapefruit. Then keep going. Far beyond that, in less time than it takes a single beam of light to cross a proton. If that sounds too fast to be physical, that's because it was faster than light itself. Nothing was breaking the cosmic speed limit. Space was breaking it, and everything inside space just came along for the ride. For a universe built entirely out of pure, undifferentiated energy, this should have been the whole story. Expand, cool, thin out into nothing. But something else was happening underneath the expansion. Something that would determine whether there would ever be a you to ask these questions in the first place. As the newborn universe expanded, it cooled. And as it cooled, pure energy began doing something energy isn't supposed to do. It started turning into matter. This is the same relationship Einstein captured in his famous equation linking mass and energy, but here it was running in reverse. Instead of matter becoming energy, energy was condensing into particles, quarks, electrons, neutrinos, a boiling, churning sea of the most fundamental ingredients physics has ever catalogued. There was just one problem. For every particle of matter that formed, the universe also produced its opposite, antimatter. And when matter and antimatter meet, they don't coexist. They annihilate each other completely, converting straight back into energy. For a brief, chaotic window, the infant universe was a battlefield on a scale with no modern comparison. Trillions of collisions erasing trillions of newly formed particles instant by instant. If the amounts of matter and antimatter had been perfectly equal, that would have been the end of the story. every particle destroyed by its opposite, a universe of light with nothing left to build a single atom, let alone a galaxy. But they weren't perfectly equal. For reasons physicists still don't fully understand, there was a tiny asymmetry. For roughly every billion particles of antimatter, there existed 1,000,000,001 particles of matter. That single extra particle in a billion is the reason anything exists at all. Every atom in every star, every planet, every living thing is leftover residue from that lopsided war, the fraction of matter that had no antimatter partner left to destroy it. We are, quite literally, made of what didn't get erased. And the universe wasn't finished testing itself yet. For the next few 100,000 years, the universe existed in a state that would look nothing like the night sky we know. It was opaque. Free electrons streamed through space in such enormous numbers that light couldn't travel more than a short distance without slamming into one and scattering off course. Imagine trying to see a flashlight beam through dense fog. The light exists, but it never travels far enough to reach anything. That was the entire universe. A hot, glowing fog with nowhere for its own light to go. Meanwhile, deeper processes were unfolding. Protons and neutrons had already begun fusing into the simplest atomic nuclei, hydrogen and a small amount of helium. But they weren't complete atoms yet. They were still missing their electrons, which were moving too fast, and the environment was still too energetic for a stable bond to form. The universe needed to cool further before it could finish the job. That moment finally arrived roughly 380,000 years in. As the temperature dropped to a few thousand degrees, electrons slowed down just enough to be captured by atomic nuclei. For the first time, neutral, stable atoms existed, and the effect was immediate. With free electrons suddenly locked into atoms, there was nothing left for light to scatter off of. The fog didn't fade gradually. It lifted everywhere, almost at once. Light that had been trapped since the very beginning was finally allowed to travel in a straight line. That release is not a theory we take on faith. We can still detect it. It has cooled and stretched over billions of years into faint microwave radiation, arriving from every direction in the sky, and we can point instruments at it and measure it directly. It is, in effect, a photograph of the universe at 380,000 years old, the oldest light that will ever reach us. But the story doesn't end with light escaping into a newly transparent universe. That universe was still almost entirely gas, smooth, simple, and, on its own, incapable of producing a single planet, star, or person. Something had to go wrong with it first. If the early universe had cooled perfectly evenly, it would have stayed a featureless mist of hydrogen and helium forever. No stars, no galaxies, no structure of any kind. Fortunately for us, it wasn't perfect. Buried in that first fraction of a second of inflation were tiny quantum fluctuations, regions infinitesimally denser than their surroundings. Differences so small they're measured in parts per 100,000. Stretched across the universe by inflation itself, these tiny imperfections became the blueprint for everything that followed. Gravity did the rest. Slightly denser pockets of gas pulled in more material than their surroundings. That extra material made them denser still, pulling in even more. Over hundreds of millions of years, thin threads of gas collapsed into filaments, and filaments collapsed into clumps dense enough to ignite. The first stars switched on. We have no direct footage of this moment, and we never will, but we can trace its consequences all the way to the periodic table hanging on a classroom wall. Because inside those first stars, something new began happening. Nuclear fusion, converting hydrogen into helium and eventually forging heavier elements, carbon, oxygen, and beyond, one collision at a time. Elements that did not exist a moment after the Big Bang were being manufactured, atom by atom, inside stellar furnaces scattered across a young and expanding cosmos. Every element heavier than iron would require something even more violent, the death throes of massive stars collapsing and exploding with enough force to fuse atoms together in the final seconds of their lives. The oxygen in your lungs, the calcium in your bones, the iron carried in your blood right now, none of it existed in the first second. All of it was manufactured afterward, inside stars that lived and died long before our sun ever ignited. Here is what makes this story unfinished. We know, with real confidence, what happened after that first second. Inflation, the matter-antimatter imbalance, the release of the first light, the birth of stars. Each step is backed by measurements we can point to, radiation we can detect, particle collisions we can recreate in laboratories on Earth. But the very first instant, the trigger that started all of it, remains genuinely unknown. Not unknown the way an unsolved math problem is unknown. Unknown in a way that may sit right at the edge of what physics is currently able to describe. And the far future carries its own open question. Some models suggest the universe's expansion will eventually slow and reverse, pulling everything back toward a final catastrophic collapse. Other evidence, including precise measurements of distant exploding stars, points somewhere stranger. An expansion that is not slowing down at all, but accelerating, driven by something scientists can measure the effects of, yet still cannot fully explain. If that acceleration continues, the future isn't collapse, it's dispersal. Galaxies drifting beyond each other's reach. The night sky, tens of billions of years from now, slowly emptying out. Two very different endings. And right now, no one can tell you with certainty which one we're heading toward. What we can say is this: the same universe that spent nearly 14 billion years assembling stars, elements, planets, and eventually a species capable of asking where it all came from, is still writing its own ending. You are not separate from that story. You're the part of it that's currently awake enough to notice it's happening. So here's the question worth sitting with. If the universe's beginning is still unexplained and its ending is still undecided, which mystery do you think we'll solve first? Leave your theory below. We'll be here, tracking whatever comes next.